I'm welcoming to everyone for this case study session design of tuned mass absorber. It's a case study is taken from Star Trace Private Limited as Chennai. Myself N Venkatesh working as assistant professor in aeronautical department SNS College of Technology Coimbatore. Is a turned mass damper, also known as harmonic absorber or seismic damper, is a device mounted in structures to produce the amplitude of mechanical vibration. Their application can prevent discomfort, damage, or outright structure failure. They are frequently used in power transmission, automobiles, and buildings. In the overview lesson, vibration is the study of the repetitive motion of objects. Vibration is caused by anything that oscillates and it's transmitted through continuous media when elastic bodies such as spring, a beam, or a shaft are dispatched from the equilibrium position by the application of external forces and then released they execute vibratory motion and the vibrations caused by a system affect other systems unless the systems are separated. This is the cause of vibration is earthquake or seismic activity, vibration created by strong wind, unbalanced force in the system, external excitations update on the system, elastic nature of the system, dry friction between two melting surface cause vibration, and defects in assembly of machines such as broken welds, loosely fitted bolts. Here is the effects of vibration is a desired effects of vibrations in a musical instruments, compactors, vibratory conveyors, shakers, stress relieving, hoppers, and shavers. Is undesirable effect of vibration is unwanted noise, losing of the machine parts, excessive stresses induced in the system. Vibration creates a rapid wear of machine parts. Due to heavy vibrations, it is difficult to get exact and correct reading from the instruments. Structural vibrations may collapse the structures such as building, bridges, etc. Excessive vibration is harmful for humans. It's a method of reducing vibration. So removing external excitation if possible. There are certain advanced methods available to reduce the vibrations to required level, and these are: first one is vibration isolator, the second one is vibration dampers, third one is a vibration absorber. Why we select vibration absorber? Ease of design, avoids resonance, ease of modification, number of effect of temperature on working, less initial cost, less modification cost in comparison, compact in nature. This is objective in this case study to reduce the vibration in a primary system by adding a tuned mass vibration absorber to the system so as to avoid resonance and to achieve optimized performance of machine or equipment. So how it works? The principle is that if a system has undesirable vibration at an operating frequency which approaches its natural frequency, then to avoid vibrations, a secondary system having its natural frequency equal to the operating frequency is coupled to the primary system to reduce its amplitude to zero level. This is the small diagrammatic representation of a principle of this working. Here is the absorber and the main systems are connecting with the spring that indicates K1 and K2 is a spring coefficient, and F sin omega t it will represents the wavelength, and x1 x2 as a displacements. This is a design procedure for a vibration is a 1 by 2 by 3 E1 I1 and M1 L1 cube the power of, where Fn is the natural frequency of a primary system, M1 is the end mass of primary system, E1 is the modulus of elasticity of primary system, and I is the moment of inertia, and length of the primary section it represents I. Here is the session 2, similar that F1 is equal to Fn2 is equal to Fn. This is the excitation. This is the procedure of calculation of natural frequency of a primary system. The natural frequency of primary systems will explanation in a turn mass dampers stabilize against violent motion caused by harmonic motion. A tuned damper reduces the vibration of a system with a comparatively lightweight component so that the worst case vibrations are less intense. Roughly speaking, practical systems are turned to either move the main mode away from a troubling excitation frequency. Given a motor with a mass M1 attached via motors mount to the ground, the motors vibrates as it operates and the soft motor mounts act as a parallel spring damper K1 and C1. The graph shows that the effect of a tuned mass damper on a simple spring mass damper system excited by a vibration with an amplitude of an unit of force applied to the main mass. An important measure of measurements is the ratio of the force on the motor mounts to the force vibrating the motor. This assumes that the system is linear, so if the force on the motor were to double, so would the force on the motor mounts. The blue line represents the baseline system with a maximum response of 9 units of force at around 9 units of frequency. The red line shows the effect of adding a tuned mass 10% of the baseline mass. Here is a D1 measure the mass of the beam and the D2 is a mass per the unit length. Here the height of the two peaks can be adjusted by changing the stiffness of the spring in the tuned mass damper. Changing the damping also changes the height of the peaks. In a complete patient, the split between two peaks can be changed by altering the mass of the damper. The back line shows that the baseline response. Now considering the blue line shows that motion of the damping mass and the red line shows that the primary mass. Here is the mass of effective length is equal to effective length into mass per unit length. End mass of the beam is a product of 0.2357 and mass of effective length. So calculation of natural frequency is from the equation of basic frequency equation is equal to 1 by 2 pi is the product of the 3ei divided by m1 L1 cube the square root of. Next is the procedure of calculation of natural frequency of a secondary system. It's A and B are decided material for secondary spring by considering its modulus of elasticity. Decide the cross section of the secondary spring, and third one is the calculate moment of inertia of the second spring. And the D and E, the fourth one is the decide length of secondary spring through experimentation, and the last one is from values of frequency, moment of inertia, Young's modulus and moment of inertia, calculate the mass using M2. Here is the validation on the experimental setup. Connect F50 analyzer, setup negative software, place exciter at the end of primary system, place accelerometer at predetermined position, connect oscillator, connect secondary system to primary system. It's the start fit analyzer, and the final one is the start oscillometer. It's a forward to a set oscillator at natural frequency of primary system. Take readings for primary system without a secondary system and connect the secondary system and take readings once again. Compare readings A, B, C. This is the graphs. This graph represents the turn mass dampers widely used in production cars, typically on the crankshaft pulley to control torsional vibration, and more rarely the bending modes of the crankshaft. They are also used on the dive line for gear wind and elsewhere for other noises of vibrations on the exhaust body. Suspensions or anywhere else, almost all modern cars will have one mass damper and some may have 10 or more. The usual design of damper on the crankshaft consists of a thin band of rubber between the hub of the pulley and the outer rim. This device, often called a harmonic damper, is located on the other end of the crankshaft opposite of where the flywheel and transmission is. An alternative design is the centrifugal pendulum absorber, which is used to reduce the internal combustion engine torsional vibration on a few modern cars. All four wheels of the Citroën is incorporated a tune mass damper. So, mass damper will be used in a spacecraft. Our proposal to reduce the vibration NASA's area's solid fuel booster has to be use 16 turned mass dampers as a part of design strategy to reduce peak loads from 6G to 0.2G. And these are the equipments used in FFT: analyzer, exciter, oscillator, accelerometer, and navigate software, and weighting machine, and spring with the mass end. And so dampers are used in the wind turbines. A standard tune mass damper for wind turbines consists of an auxiliary mass which is attached to the main structure by means of springs and dashpot elements. The natural frequency of the tuned mass damper is basically defined by its spring constant and the damper ratio determined by the dashpot. The tuned parameter of the tuned mass damper enables the auxiliary mass to oscillate with a phase shift with respect to the motion of the structure. In a typical configuration, an auxiliary mass hung below the nacelle of a wind turbine supported by dampers or friction plates. So, dampers in buildings and related structures, which are huge concrete blocks or steel bodies mounted in a skyscrapers or other structures. These are the systems of oscillator and navigate software and weighing machine, and primary and secondary systems are connected in this slide. And the application of these in reciprocating and machines. So vibration absorption in there is a transmission lines will be shown in here. Is the analyzing of comparing unbalanced and balanced mass analysis system. Here would be used for measurement of mechanical human sources and wind, and also using the vibration body and what are the frequencies will be generated. This all will be done from this slide. And the next one is the turned mass damper is introduced as a part of suspension system by Reynolds Nissan. In the production of car companies, the turned mass dampers are widely used in crankshaft pulley to control torsion, vibration, and more rarely the bending modes of the crankshaft. They are also used on the driveline for gear wine and elsewhere for others. A four wheels of a Citroën Suit 2CV incorporated a tune mass damper of very similar design to that used in Renault. So, our proposal of will be reduced. NASA's area solid fuel booster was to use 16 ton mass dampers as a part of design strategy to reduce peak loads of 6G to 0.2G. The tuned parameter of the tuned mass damper enables the auxiliary mass to oscillate with a phase shift with respect to the motion of the structure. In a typical configuration, an auxiliary mass hung below the nacelle of a wind turbine supported by dampers of friction plates. So, unwanted vibration may be environmental forces on a structures such as wind and earthquake by seeming in focus on vibration. This is our conclusion. The use of the turned mass vibration absorber easily and effectively enables us to protect primary system from undesired self-generated or external vibrations by avoiding resonance, and thereby leads to optimize the performance of primary system. And the final one is mainly focus on the vibration is how to affect the wind. The force of wind against tall buildings can cause the top off. These motions can be informed awaying, twisting, and can cause the upper floors of such buildings to move. Certain angles of wind aerodynamic properties of a building can accentuate the movement and cause motion sickness in people. And the final one is, however, during their lifetimes, here high rise and slender buildings may experience natural frequency changes under wind speed, ambient temperature, and relatively humidity variations, among other factors, which requires a robust and The tuned parameter of the tuned mass damper enables the auxiliary mass to oscillate with the phase shift with respect to the motion of the structure in a typical configuration, and auxiliary mass hung below the nozzle of a wind supported by a friction. So this is a case study for a topic for design of tuned mass. These data are collected from a Star Trace Private Limited, Chennai. It's references of the some sites showing the what are the causes will be occur in the mechanical vibrations. So thank you.